So now our second speaker is Farzad Aryan from University of Göttingen, and he will talk on higher moments of distribution of zeta zeros. So please.
All right, thank you very much for giving me this opportunity. I'm going to talk about this project I did while I was at IPM last year. So now let me begin. Consider this function b of s equal to sum of, let's consider this polynomial basically. Sum over n depends on the variable is s here in the complex plane. These are generally, we call them Dirichlet polynomials. I would set s equal 1/2 plus it and end up with a one variable function. Basically, I'm more interested to look at this polynomial just on the half line. And why we are like interested in this polynomials in analytic number theory mostly, because they are like why basically I want to explain why they're important subject of studies. The reason is they often mimic the behavior of L functions, like zeta function, for example, which is an important subject of study in that field, has a representation in terms of Dirichlet polynomial. L functions in general, all of them, they have a series representation. You can truncate, you can cut the sum through like enlarge enough and look at what's remained. And it would give, it doesn't have all the properties of the original function, but it would give you some ideas. It does mimic, it does mimic the behavior. For example, here, look at the zeta function. There's this classical approximation of it. Zeta 1/2 plus it is this finite sum here, minus these two terms that, this is basically error term, it's small, and this guy gets a small if t, this little t, start to get around the size t. So if I assume that my little t is about the size t, I'm end up with a good approximation prima zeta function, which error term is 1/√t. Which, and this, note that the size of this guy is, this length of the Dirichlet polynomial is in like n smaller than t, and this is important. So in many of our problems that we have in theory of L functions, like they come down to understand one way or another, one like Dirichlet polynomial for a certain coefficient and in some ranges. And I will give more example of like, I will give you like, I gave you the like how the zeta would be represented in terms of that approximation. I'll give more about it. So what I'm going to do, I'm going to separate the real part and the imaginary part of this Dirichlet polynomial. We look at them separately first. And now I have a real part and an imaginary part. And so basically functions from R, it's real functions. If I want to understand, like say, consider real function, I want to understand the behavior of this guy, a function I have. So our natural, like what we do is usually we ask some statistical questions. Like we ask, what is the mean of this function in the interval, like t and 2t, and t be a parameter? Or what is the variance of the function? And like we usually normally ask them all with respect to the Lebesgue measure. We can also add to this, we can build up sometimes measures that are more relevant to underlying questions. I'm going to be like explaining all this more as we proceed. In general, though, we are asking what is the value distribution of our function, and in our case, we got to ask what is the value distribution of a Dirichlet polynomial on the half line. So now, let me tell you how much we can answer like the question about what is the mean or what's the variance of this Dirichlet polynomial. For the mean, so if I consider the Dirichlet polynomial very general form, it's we can calculate the mean, but it doesn't give us much. So if I integrate b of 1/2 plus it, I'm going to have integrating by terms, all the terms that have it in it, they oscillate, and I end up just with the constant term. And here I'm assuming that none of the coefficients are like going crazy to like dominate the sum. Some assumption like this put it, but important point is mean doesn't give much. Mean with respect to the Lebesgue measure, obviously. But knowing the variance start to give important information. Knowing the variance start like to be useful. And since it's useful, problem comes with it, and you cannot calculate the variance for it. I mean, we don't have the technology to calculate the variance for a general Dirichlet polynomial. So, but let me tell you when we can calculate the variance. If we want to calculate the variance, the length of the Dirichlet polynomial means this guy, m. It should be smaller than the length of the integral. Like m should be, say, t divided by log t, something like that. This is the case that we can calculate the variance, and it's a Montgomery 1 theorem. Basically, it says the variance of this guy is this sum. But this is only like works if like m is like, say, little of t. It means the length is smaller than t. If the non-naturally question you ask me, like what happens if the length of your Dirichlet polynomial is bigger than t, bigger than the length of the integral. In that case, you need to know about the shifted convolution of the coefficients of the Dirichlet polynomial. Like for example, assume the b of n is the characteristic function of the primes. Means it's non-zero when n is a prime and 0 elsewhere. And you would like to look at the Dirichlet polynomial that is supported on primes, the support of the sum, I mean. If you take this one, this Dirichlet polynomial long enough to understand the variance of its values, how the variance is calculated, you must know this guy, which this guy is basically the twin prime conjecture. When I'm right, like consider b of n be a characteristic function of a prime. So a point I like to make is when you want to take a variance of long Dirichlet polynomial, and if you want to use this technology of knowing about shifted convolution sum, then knowing about the variance is developed by Goldstein and Gonek. But the important point is often it turns out to a harder problem than you originally have. Like I have a Dirichlet polynomial with supported, say, the sum is supported on primes, and I want to understand a little bit about it. Then if I want to understand that little bit, I don't want to come here and assume the twin prime conjecture, and not only I have to assume the twin prime conjecture in this popular form, I have to assume the twin prime conjecture to be able to say something. For my original polynomial, I have to assume the twin prime conjecture in its strongest form, means like I have to have a main term for it and power saving on the error term. So this is my point, that lots of times this turns to a harder problem than the original one. You may ask, if you don't like care, what about higher moments other than variance? You can apply the same logic as you go moment. If you want a higher moment, your Dirichlet polynomial should be shorter and shorter. Like you can go fourth moment if your Dirichlet polynomial has length around square root t, and fifth moment for if t to the power 2 divided by k. As you see, as k gets larger, I can just like have information about shorter and shorter Dirichlet polynomials. And so far, I'm talking all this with respect to Lebesgue measure. It means like I give an equal chance to every point on the interval I'm considering. So to understand our function better, sometimes we can change the measure. Like we don't need to have always look at it with respect to the Lebesgue measure. So if I, for example, I'm interested in distribution of values of b of 1/2 plus it on the half line, and I just want to like look at this guy when t equals to imaginary part of zeros of Riemann zeta function. So imagine like t is equals to gamma when gamma is hit the imaginary part of the zero of Riemann zeta function. So like that's where I'm like focused. Then I don't have, it's a bit, it's better instead of using Lebesgue measure. The Lebesgue measure gives equal chance to every point. So like zeros and non-zero, it does not distinguish between them. So maybe I should put a measure in that highlights these zeros. Then you may ask, how would you like build this thing? So imagine I have a function like this, which is like not very large elsewhere, but when it's like hit the zero, you see a peak on it. So like most mass of this function, let's say, is around zeros. Probably for my purpose, would be better to use this guy as a measure and look at the mean and look at the variance and so. So like my goal, my dream would be to completely understand something like this with respect to that measure. That would give me a lot of information about what's going on. But as I say, there's tons of limitation comes with it. So let's talk first about how to like kind of build up such measure that highlights a certain value for certain points on a line. And then we talk about how much possible it is to look. So what I'm going to describe is a commonly used method, like all over the place in analytic number theory, and they call it the modifier method. Basically, what they mean is that we use a Dirichlet polynomial that highlights the property that we're interested in. So let me tell you like how we make this measure first. So the build up a measure always in the modifier method or whatever, it's always again using Dirichlet polynomial. So I have another Dirichlet polynomial other than my original one. A of s equal a n to the power minus s. Then I define a measure of the interval is that how much of values of this Dirichlet polynomial is centered at that interval. So this whole thing, on the denominator, I integrate the whole thing to get the whole mess. And in A and B, I just integrate that part in the A and B. If we put A, for example, A of s equal to 1, the constant function, then I'm going to end up with the probability version of Lebesgue measure. It's like you have an interval of length t, and you divide by t to normalize it. So this is important because I'm going to like really stick to this for the rest of the talk. I'm going to like really work mostly with the measures that I built this way. Let's give an example of one of this function that highlights that would be look like the picture I show you, that highlights the values of the zeros of Riemann zeta function. So we build this Dirichlet polynomial as a coefficient. We use the Liouville function. Liouville function is minus 1 on 1 and is minus 1 to the power of a number of prime divisor of 1, the number of prime divisors of n. So, for example, lambda of 1 is just equal to 1, but lambda of primes is equal to minus 1. Now, lambda of product of 2 primes is equal to, again, it's switching back to plus 1. Product of 3 primes minus 1. So if I put this in the, if I pick this arithmetic function as my coefficients, it's known that the final function, A of s, would highlight the zeros to some degrees. The length is very important. The longer you get it, it's like the peak around 0 would go, like it gets narrower and narrower. Look at this. So let me go back to this picture I showed. Because I have a little peak around each 0. So the longer I take that length of that Dirichlet polynomial, the variance of this guy would be smaller and smaller. So it would like go higher and it like really look with more and more look like the characteristic function of zeros. So this is one example of this how we can build up measure like that. And is there a question? And so obvious question is that, so when you don't work with Lebesgue measure and work with these measures that you take from Dirichlet polynomial, how much information you can get? What are your limitations? So if I like back to definitions of the B, my original Dirichlet polynomial, and A of S be the modifier or the measure I'm using, we can take a look at the first moment. There is no problem if the length of the Dirichlet polynomial A here is smaller than length of the integral. So I can't look at the mean of this arbitrary Dirichlet polynomial B if the length of A is smaller than T, which would be length of integral, length of the area under consideration. So that's the only if, which is like, which gives you tons of limitations. So going forward, when I'm writing B of 1/2 plus IT, d mu of A, that's what I mean by it. It means that I multiply B by the square of this guy and integrate. So now this guy would amplify some values of T rather than the others. So at the end, I'm studying my function B more on those points that is amplified by A. So it is going forward, it's like I'm writing this thing as B of 1/2 plus IT d mu of A, mu of I get from A. And one comment is that when we, in practice, we don't like integrate, like we usually use the smooth bait here in the integral to close the boundaries of integral from T and to T. Because the reason, like probably things would work with just the integrating this way, but it makes the technicality much easier when you use a smooth bait. So as I said, the first moment is calculable as long as the length of the measure or the modifier is smaller than T to the power smaller than T to the 1 minus epsilon, basically. But unlike the Lebesgue measure, the mean gives you important information. So as soon as a limitation hits, you know that you are like up to something. So I talked about the modifier. Oh, sorry. Sometimes they call it resonance method. They call the resonance method in terms of when they were looking at large value of Riemann zeta function. I think this is the name Sandra Rajan picked, but it may be even older. So you probably ask, how would you use the mean of such thing? How would you it would help you. So what I do is say, I have a Dirichlet polynomial. I'm interested in large values of that. And my question is that how large it can get. So I'll go and pick a measure that I know it probably is more supported on the large value of that Dirichlet polynomial or that L function. Then I calculate the mean and say I get a sigma. I get a number. As expected, it should be a large number, as large as if you pick just a random measure or a Lebesgue measure. Then, immediately from this, and the fact that we define these to be a probability measure by dividing by the whole mass, I can say there exists T such that my Dirichlet polynomial has values larger than sigma. So that is like one immediate application that lots of people use. So, for example, sound, which call this the resonance method, use this and prove that there exists T, that the values of the Riemann zeta function gets bigger than square root log T divided by log T. If this is a little strange, imagine like it's a zeta of 1/2 plus IT is bigger than arbitrary power of log t. And I want to say something for that. So the result of sound being improved by Bondarenko and Sip. They add this term, log t today. And so they use the resonance method that I explained, then they add some new ideas to that. It's a beautiful paper. And it proves that the zeta function gets large. And my conclusion is that calculating the mean with respect to measure other than Lebesgue is pretty useful. It comes down to give good results. But so immediately you would ask me, so what about the variance? Like you have the first moment, you have the mean, what about the variance? So there is a trivial bound, obviously, on the variance. If you have the mean equal to sigma, the trivial bound on the variance is sigma to the power 2. That's what I mean by it. To see this very quickly, this is obviously positive because I'm integrating something positive, and I'm considering real functions here. And I open it and I end up with this. I know this term because I have the mean. That's where I'm using the mean, and that's where I'm using also this the mu. The fact that mu should be probability measure. End up with this, and since positive, I get the variance of my function is bigger than the mean to the power 2. So that's what I call the trivial bound, the variance. But you may ask, so can you do better? So if we could, that would be wonderful. It would solve tons of problems that like been open for a long time. The things with variance gets really bad. If you want to have an estimator, if you want to estimate it, like calculate it, you need to know the shifted convolution sums of the sequence A. You need to know when you convolute A with B, shifted by A again. And these are like if I say it's some normal sequence, like say A is supported on primes and B is like, let's consider B be like the Liouville function. These are going, if you really want to estimate these folks, these are going beyond GRH, generalized Riemann zeta, generalized Riemann hypothesis. It's like, and there is not, mostly they believe they are random sequence and they cancel, but I don't think there's like much, because it's so way down of what we can prove that I don't think people are much interested to like even figure out what will happen with the sequence. But the important point is that it gets like even crazier problems that like I want to know a little bit about my behavior of the statistical behavior of one Dirichlet polynomial. I cannot go end up like assuming things that are harder than twin primes and Chalo conjecture and like a strong variation of them. So this is important to find a way around this instead of like assuming shifted convolution sums and like assuming I know about this sequence in this sums. If I can find a way to somehow get certain estimate of the variance, which in some cases it's what I'm going to demonstrate is it is possible to beat the trivial bound on the variance. So let me get a specific because I want to explain it, and and it would also demonstrate that why we are interested in these values of a Dirichlet polynomial. So define Z alpha of 1/2 plus IT as sum over primes. The Dirichlet polynomial goes up to t to the power alpha. That's where the alpha comes. These terms normalize it. And this guy, 1 minus log n divided by alpha log t, is a smooth fade that cut the sum, basically. It slowly goes from 1 to 0. This object I have is somehow an approximation of the logarithmic derivative of the Riemann zeta function. So keep that in mind. I'm approximating logarithmic derivative of the Riemann zeta function. And it does carry Not all the properties of that, but some of it. So the fact that length is t to the power alpha is important. For alpha smaller than 1, we get the, if I integrate with the Lebesgue measure, probability version of Lebesgue measure, this is 0. So the mean is 0 with Lebesgue. The variance for alpha smaller than 1 is possible to evaluate, and the variance is 1 divided by 3. And what I'm going to do, I'm going to separate the real part and imaginary part to make the calculation easier. For alpha equal 1, I'm going to drop the indices when I'm like giving the results I have. I'm going to drop the indices because there's like not very necessary. And so why this guy is interesting? Because, for example, if you can prove the real part of Z, it's get bigger than 1 sometimes, then you prove that there is no Landau-Ziegler 0. Equivalently, if C2, which means alpha equal 2, bigger than 1/2 would give you the same thing. It's a little bit like this guy would prove that there are gaps smaller than 0.5 between the zeros of Riemann zeta function. This guy would precisely reject what is known as the alternate hypothesis. They both, though, gives you the important, they both give you the important, very important application that there is no Landau-Ziegler 0. And if you guys catch Ali's talk, he was talking about how important this is for the class number problems and things that comes from algebraic number theory. So as I said, having CFT bigger than 1 is equivalent to having gaps smaller than half the average gap between 0 and Riemann zeta function. So let me give you a heuristic. Here I want to give you heuristics that what would be people that do probabilistic analytic number theory, how would they kind of guess what would be the distribution value of Z. So if you note that the support of the sum in the definition of Z was on primes here. This function lambda van just limit my sum to primes. So how do people look at it is that this, then they look at primes p to the power it as an independent random variables. And you have some of independent random variables, they say that we expect it to be normally distributed. And what is this normally distributed means here is like, for this sake, is like, look at this, it gets large. It's expected to get large, the Z of alpha. And so how much do we know about the real and imaginary part of Z alpha? As I said, the real part, like if you can prove a little bit, like even like C of t is bigger than 1, which if you accept the heuristic, you should get arbitrary large, bigger than every k. If you just can't prove it's bigger than 1, then you're proving the excellent theorem. For the real part, we have a little bit more because we can relate the real part to the distribution of zeros of the Riemann zeta function. So let gamma denote then imaginary part of the site 0. Assume the Riemann hypothesis that says all the non-trivial zeros are in the half. Then I have this formula for the real part of the Z alpha. If it's a little ugly, look at it this way. This formula counts how many zeros are close to t, basically. C of t, just if I have 5 zeros around t, very close, then I get 5 in the sum and minus 1 over alpha, which is the factor comes from the average value of the real part. So keep in mind that the real part of that is kind of counting the zeros that are in the vicinity of t. And look at the accumulation of them. Obviously, the parameter alpha is important, plays a role. So yeah, now it's probably a good place to say how much is known about distribution of zeros, because I said that, I already mentioned that if you know good amount, you will be able to solve a good problem in algebraic number theory about the class number problem. And I mean, proving there is no zero zero, it's perceived to be a very hard problem between like analytic number theories. But how much we know and how much is conjecture about the distribution of zeros, Montgomery in 73, he conjectured that the probability of getting gaps is smaller than beta. So imagine gaps smaller than beta. And normalized gaps means that multiply them by a number that the average gap between them equal to 1. So the probability of getting gaps, average gap smaller than beta is given by this function. And this probability distribution function has a similarity with the probability distribution of the eigenvalues of certain matrices, which at the time suggested that if people looked more into the spectral theory, they may learn something, but not much came out of it. The important thing about his conjecture is it does prove that gaps getting arbitrarily small with a low probability, but it would get arbitrarily small. And therefore, he would reject the existence of lambda equals zeros, as I said, and that was his motivation for looking at that. And how much we know about the gaps between zeros, under the assumption of Riemann hypothesis, Montgomery and Lisko, they proved that there are gaps smaller than 0.5179 times the average gap. And there are like tons of authors between this and the best result, which is due to Preobrazhensky, who showed gaps are getting smaller than 51, 53, 96. And the threshold that is important is 0.5. You want to beat 0.5 to prove there is no lambda equals 0. That's the result of that comes from the work of Kundry and Imaniak. That proving you have enough number of gaps smaller than 0.5 would reject the possibility of lambda equals 0. It's important thing is the method they use is like, as they mentioned in the papers, is a kind of a dead-end method. Means that with their method, you can never beat 0.5. This is an important thing to note. So, as I said, C alpha has tons about the existence. It gives tons about distribution of zeros of Riemann zeta function. For alpha equal 1, I can look at the variance of it. This is possible to calculate with respect to Lebesgue measure. It gives you 1/6, which means that keep in mind that like my dream would be to prove C of t is bigger than 1. Now, with this estimate from the variance, I can find t such that with positive Lebesgue measure that C of t is bigger than 0.4. Now, we drop the Lebesgue measure. We go pick up something that highlights the value of zeros and obviously highlights the accumulation of zeros. If I apply that and look at the expectation of C of t with respect to this measure, I get 0.666, which is an improvement obviously to 1/6 here. So this result gives me there must be t that's value of C of t gets bigger than 0.666. And this is just from the first moment. What about the variance? What we can get for the variance? And okay, this important point that this is already better than what we can get from the Lebesgue measure. So this is a corollary of a theorem I proved that for the variance, c to the power 2, with respect to this measure, like getting from the lambda of n, the variance is bigger than 0.4666. And this integral above, let me remind you, it just means this guy. D mu lambda is this guy. So probably you want to compare it with what the trivial bond gives. So this immediately shows that we get t that C of t bigger than 0.68. So a little bit better than 0.666. And the trivial bound, which would be a square of 2/3, 6666, is like something around this guy, and you can see that about 2 divided by 100 it improves. This result improves what you can get trivially for the variance by that much. Now let's talk about the imaginary part. As I said tons about the real part. Real part is much better understood than the imaginary part. The imaginary part is much more mysterious because it has more oscillatory nature. But let me say what we know, and let me explain why it's harder to get results on the values of imaginary part. So first of all, when I integrate it with respect to damage, I get 0. So the mean, if using mean to get a bound for variance, it gives me trivial. It gives me 0. It gives me like nothing. If I use Landau-Gunek formula for an average, the imaginary part on zeros of, this is possible with Landau-Gunek formula to find this average on the numerator. So now I want to average the value of the imaginary part on the zeros of the Riemann zeta function, but with a little shift. And this is the shift, 2 pi d divided by log t. Let's go a little bit to the right of it. Obviously, if you put, so this is calculable, and this is equal to this integral. If you put d equals 0, again you get 0, which doesn't give you anything. But if you shift, if you put, for example, d is equal to 0.41, you get, on average, the right-hand side is about 0.27, which shows that there are points that the imaginary parts gets bigger than 0.27. And this is using Landau-Gunek formula. A Landau-Gunek formula would be for 1 minus epsilon. You cannot, so if the imaginary part of Z2, when alpha is equal to 2, you cannot use the Landau-Gunek formula to estimate that. If you could, that had a like very, it's I think one of the easiest way to disprove there are ziggo 0 is to look at Z2 and average it over zeros. That would do the job. So imagine, so I said that the real part has a very tight connection to distribution of zeros of Riemann zeta function, and it would get large values when you have accumulation of zeros. Imaginary part has ties to the famous S of t function. S of t is the deviation from the expected value in the zero counting function of the Riemann zeta function. What I mean by that is, if I count how many zeros are up to height t and subtract what I expected to be, S of t gives you this basically error. Look at it this way. How it is connected is a famous theorem of Selberg that says that S of this polynomial, the imaginary part of this polynomial, would approximate S of t very well. This is basically what does it mean. It means on average, it's a good approximation of S of t. So that's a bit we know about the imaginary part, but mostly it remains a little more secretive than the real part, I have to say. So using this theorem, Selberg went on and showed that higher moments of S of t matches the moment of the normal distribution, Gaussian distribution, which if you pay attention to the speculation I mentioned, it does to some level confirm. It's a very, very genius like method. There's tons of parts. You put tons of pieces together to get to that. Because I mean, yeah, if you want to like calculate the Kf moment, you need your Dirichlet polynomial gets shorter and shorter, and it makes that approximation difficult, and you have to find a way around all that. And as we proceed, I'll give one more important properties of the imaginary part. But let me show you first what I can get for the big values of the imaginary part. So this is our corollary. It says that imaginary part, with respect to measure I get from the Liouville function, the variance of it is getting bigger than 0.110. And so another important point is that using this guy, mu of lambda, is not the best it's not the best modifier for it. It's obviously, that's a very good modifier for the real part, but it's not for the imaginary part. But still, this, what I'm getting from this is imaginary part is getting, sometimes we get 0.3162, which is an improvement that to what I can get from the Landau, applying Landau-Gonic formula. So this is important. Even though my modifier is not the best, still I'm beating the use application of Landau-Gonic formula for the large value of imaginary part. So probably you say, oh, so why did you use a better modifier? So when I was looking at all that, because of the proof, not because of some other like a explanation, because of technicality and proof, I found this generalization of the Liouville function that seems that that gives a good modifier for the imaginary part of this function. So consider if n has this prime factorization, define it lambda 2 of n minus 1 to the power number of prime divisor divided by 2, and that's the integer part of it. It's better to explain probably with the example. Lambda 2 of 1 is 1, lambda 2 of primes is also 1, but lambda 2 of product of 2 primes is minus 1, as well as lambda 2 of product of 3 primes. And when it goes to product of 4 primes, it switch back to 1. If you want to compare it with the Liouville function, lambda of Liouville function over primes is minus 1. So it changes every 2, with every 2 prime factor it changes. And this L function, if I put this guy and define the L function, is pretty mysterious. I couldn't find much about it. But why I'm saying that I don't have a philosophical reason, this probably would explain it, because, for example, the L function is defined with the Liouville function is basically zeta of 2s divided by zeta of s. So it makes sense that it has large values when s is a zeros of Riemann zeta function, because the denominator gets 0 and explodes. This guy, it's not, we don't have such a thing for this guy, for the lambda 2. We don't have such a neat formula for it that we can say, okay, because of this, it would amplify the values of the imaginary part. And so, as I promised, it would give a very good improvement to what I had in my previous corollary, which was 0.1. So it gets the variance is getting bigger than 0.466. And this would show that the imaginary part of the logarithmic derivative does correlate very well with that modifier with coefficient comes from this strange arithmetic function lambda 2. Also, for the large values of the imaginary part, it does prove the imaginary part of t is bigger than 0.68. So let me just bring back the real part and imaginary part to probably the original aim, that getting large value for these guys. So these are corollaries that come from main theorem, and it does relate them together. For example, look at this first one. If I have a good lower bound on the imaginary part to the power 2, because of this, I can get a lower bound on the real part to the power 2. And using these things, we can even say a little bit about a bit you can beat the trivial bound, because you get a trivial bound also on fourth moment. You can a bit improve those too. And as I mentioned, the goal is to beat C of t is bigger than 1. And this result shows that they basically real part and imaginary part, even in our original problem, they're intertwined, that they affect each other. So, and also keep in mind, when the power goes up, if I accept the speculation that primes are independent, or if I accept the Montgomery pair correlation conjecture, this guy should explode. This guy should go to infinity. So as moment goes up, I expect these guys to go to infinity. So the general theorem is this. It goes to look at the combination of the powers of k. I demonstrated for the k equal 2, 3, and 4 there. in the corollary. And these guys look like a complex random variable, and it's look like if you consider their pseudo moment. Obviously, if you know all the moments of a random variable, you know the distribution. Pseudo moment is like, imagine z is a random variable, and you just have z to the power k. So you don't have the absolute value of z to the power k. If you want to know the distribution, you need to have absolute value of the z to the power k. You may ask me, what is the right-hand side of this guy? It's about 2 to the power k divided by k plus 1 factorial. So from here, my question I had is that, so all these estimates that I have, does it give extra information? Like my results on variance give some extra information. Well, would the information be enough to beat that bound? Because you don't want to waste lots of times on these problems and like go around the circle, and you realize later on that there are limitations. You cannot, your information that you have is not enough to beat this threshold. So what I thought about is that, what about if I can find an analogy between random variables that they have same pseudo moments, and can they be bounded or unbounded? That was the question I was asking. So this was answered in Math Overflow, that they give you basically that you can find random variables that they have these pseudo moments, and they can be bounded or unbounded. So let me give you an example of that. Let z be x times u. X and u are independent random variables. X is positive almost surely. Assume that x is unbounded, but assume the moments are bounded. U be random variables as e to the power it, the distributor on unit circle. The probability density function comes from this exponential sum, basically a cosine sum. I have to assume a little bit that make it the PDF, but that's not important. Important point is the expectation of u to the power k gives me ak. Now I can pick ak to be around 2 to the power k divided by k plus 1 factorial and divide by expectation of x to the power k. Now, if I look at z to the power, expectation of z to the power k, or pseudo moments of z to the power k, I basically end up with desired bound. What I assume that x be unbounded is make my random variable unbounded. I could assume the x is bounded, which make my random variable bound. So here it's like a kind of a disappointing example, because it probably suggests that, well, from this information you get from the pseudo moment, you can't get enough to prove that, for example, your underlying function gets unbounded. The thing is, the difference is that if you want to make an analogy with the z polynomial that I said, the logarithmic derivative, is that the large part, the part that makes my random variables large, is completely independent of the oscillatory part. This is a thing that makes it hard to make an analogy between these two, because if my random variable gets like unbounded and I have a oscillatory part, if it gets arbitrarily positive, I would expect it to be arbitrarily negative too. But as we're looking at the formula that I put for the real part of z, that doesn't happen. It does not go. But the negative, at most it can get is like minus 1 over alpha. That's the most negative it can get. So it's like, it's hard to, I did try and I thought about it for a couple of weeks to make an analogy between this and two. It's not obvious how it can be connected. But a question remains that from the result I got from the higher pseudo moment, are those enough to suggest that C of t gets arbitrarily unbounded or stay bounded? Like, do we have enough information to make conclusion like that? That question I cannot answer. Let me say a little bit about the proof. How much time I have? I guess I have like a couple of minutes, right? So
I guess 10 minutes because you have 1 hour.
Okay. So let's say maybe 1/2 plus beta divided by log t. Basically, this means that instead of working on the one line, we go a little bit to the right. And assume Riemann hypothesis. Selberg proved this result for the logarithmic derivative of the Riemann zeta function. And if you go a little to the right, this is basically bounded, which this is not very good for us, for our purpose, because like boundedness of the variance, it wouldn't suggest to me that I would get very large results for the logarithmic derivative. But later on, Goldstein, Gonick, and Montgomery, they proved that if you get an asymptotic which depends on beta, this would be equivalent to Montgomery pairs correlation conjecture distribution of zeros between zeta zeros. How did they prove that? They used this simple identity. The absolute value of some complex number is the 2 times real part to the power 2 minus the real part of that complex number to the power 2. And then they were integrating with respect to Lebesgue measure. And this guy would disappear when you integrate the Lebesgue measure. You would throw out the information that this guy carries. But this guy, as I said, real part of the logarithmic derivative is very closely tied to the distribution of zeros. And therefore, if you assume Montgomery pair correlation conjecture, you would understand this object very well. So that's what they did. They're connecting the size of that and size of the real part. Because the Lebesgue measure of this part disappear. What I did was opposite. I changed the measure to take advantage of this part the most. Meaning that take advantage of the square of this zeta prime over zeta. And so that's why like the improvement comes out and the difference of the results. I think, yeah. So by switching, the most important point about the proof is that by switching from the Lebesgue measure to measure I get from these modifiers, then I can get the result that I show you. And yeah, rest of it is pretty straightforward. And the thing about mu of lambda 2, it's kind of, if you read the proof, it's obvious why I choose that. But if I did, for example, if I didn't have the technicality of the proof, I wouldn't have guessed that that function would correlate with the imaginary part of the logarithmic derivative. I think I stop here. It's a good time. Thank you very much.
Questions, comments?
I have a question.
Yes, sure. I cannot see the Zoom. I don't know why. But go ahead.
Thank you very much. Any questions or comments, please?
I have a question.
Sure.
So you said that you used d mu lambda 2 for the imaginary part, and it resonated with that. But so did you also use that to get the improvement for CT?
Oh, applying the mu, like modifier with lambda 2 to C of t, you mean?
Yeah.
No, it doesn't give big, like large results for C of t. It does not correlate with that much.
Oh, okay. So your first corollary was on CT, right? So how?
Yeah, first corollary was CT. Do you see it now?
Yes.
Yeah.
So how did you obtain this? Did you use a different method here to get this improvement? Because you said this was an improvement over the previous results, right?
This 0.466, it's an improvement to the trivial bound you get from the mean. There's a modifier method. Modifier method gives you the mean. Mean gives a trivial bound for the variance. But this guy improves that trivial bound. Trivial bound, so for the mean, I get 0.66. If you square it, you see it's about 4.444. This beats the trivial bound on the variance.
Oh, okay. So can you say
no one looked at these values with respect to measures other than Lebesgue. Montgomery in original papers, it looks at the C function, but with the Lebesgue measure. and he basically averaged them over the zeros of Riemann zeta. That's where he gets his original result on the simple zeros of the Riemann zeta function, like 2/3 are simple, or his result on that there are gaps smaller than 0.68 between the zeros.
I see. And I have one more comment. I think the one about, so I don't know how to spell his name, Przebrzynski?
Yeah, probably.
Yeah.
That.
There was a talk of Caroline Tornich-Butterball, and I think in a joint work with Trojan, she said that they were able to improve it, but by a very small amount. I think they also.
I'm not sure about that because they put the paper out with Goldstein and they claimed a very nice result. We were all surprised. I even accepted on face value and used their coefficient to code something because I was wanting to look at something. But a year later, they said they found there was a mistake in it. They retract the paper. What was the name of the lady you said? Tornbach?
Butterball, but this one I think it was with Trojan. It wasn't with Goldstein.
Yeah, it's like probably maybe there's a little improvement.
Yeah, I think it was a very, very small improvement anyways. It was like, again, 0.51 something.
The one they put with the Goldstein, it was impressive. It was 0.50 something. But the important thing is that method would never beat 0.5. The method.
Yeah, I know.
Like from the up, this is from the beginning.
Right. Okay, thank you.
Oh, thank you very much for your questions.
Any more questions and comments?
I have a little thing to say. My recent correspondence with Goldstein said they were going to fix this mistake with Carnage Butterball.
So they did fix it?
No, they didn't. But they're like this February, March, they were going to work on fixing it.
Because the paper was even accepted.
Yeah, but they found the mistake themselves, or somebody pointed out. But
yeah, someone pointed out.
But as you say, it's never going to beat 0.5 anyway.
No, you're never going to beat 0.5 anyway. And so when we get to the problem like that, the lots of speculations, like some people believe that sigma 0 exists. Some believe that if you want to beat that, you have to invent. I mean, these things that they're not very precise. I was talking with Sarnak like a couple months ago, and he was saying that they were working with Ivaniak on this project that they inserted GL12 function into the problem, and they said, for study zeros, let's look at the non-vanishing of this GL2. And he was saying that, at that moment, I thought we added this ingredient that is needed to solve this problem. And he was saying that, so they were working for months and months. And he said, at the end of it, after lots of work, another real character, he said, popped out that completely needed all the information we were trying to prove. So these things happens to people so much that they circle back to start from somewhere. Everyone's cynical about these problems, obviously, to be solved ever.
There is supposedly a paper, not supposedly, there exists, by someone called Josef Beck in Rutgers University. 2 papers, actually. One of them is 300 pages long. The other one you can reach from the archive. He claims to have, and it's a serious claim, to have a major improvement in this Landau exceptional zero problem.
Okay.
But it's too long for anybody to check. It's 300 pages, the technical part. The other part is 40 or 50 pages long. You can reach easily. The larger part, you can, I told at one point, a student of mine wrote to him and got the big part also. That's something, and it's a serious claim. It's not some quackery or something, okay? Maybe.
What's the name again, please?
Josef Beck.
Is B-E-C-K?
Yes. B-E-C-K. Josef, I think J.
I'm gonna look at it.
EF, he is in Rutgers University.
So
He has important.
he claims that he can prove gaps getting smaller than 0.5, or how's his?
He makes a big improvement in this zero-free region for the real character.
How? So that would prove the Vinogradov conjecture also, because any improvement of zero-free region over real character would prove that the character sums getting small. Is it like a very classical result of a Russian guy? I think his name is Rodosky. He proved that if you slightly improve the zero-free region for LSK, then you have the Vinogradov conjecture on that the smallest quadratic non-residue is smaller than q to the power epsilon.
I must have it someplace. Well, I can immediately check from. I have it in my office computer, not here at home.
Mm-hmm.
But I can check out archive for Beck. Let's see what he gets. He makes a big improvement, although it's been some 10 years or so and it's not published.
Oh, and it's not published. So I mean, you know, Zhang also claims that he has a paper on archive, claims that he solved the zero problem, and he's not retracting it, and people don't know why he doesn't retract it.
This is not that people found mistake. It's too long to check, and he wants to find a student who is willing to check this 300 pages.
But is his idea clear what he's trying to do?
I found the paper. If you write Joseph Beck.
But I'm going to check this guy.
The result, let's see, he claims, he proves L of 1 chi delta. Delta is larger than some large number, e to the 10 to the 100, is greater than 1 over log delta to the power 146. And then he gets...
That's basically what you need for the class to like have a very good class number.
Yeah. He gets his... this is like from the first page of his paper, which is... I don't know how many pages is this. 72 pages is the first paper, 200 or 300 pages is the justification for this stuff. So it adds up to something like 300 pages.
I cannot find him.
If you're interested in this Landau-Siegel zero business, this is something to look at least.
Yeah, of course, yeah. I did look at Zhang's paper on archive a bit. Yeah, but they know where the mistake is there.
Whose paper?
Yichen Zhang that proved the bounded gap on your work with the So he has a paper claimed the Siegel zero before bounded gap. He claimed that he proved the Siegel zero problem. The paper is still on archive. And some people complain that he should retract it because he's very famous and people may take it serious. But I know for a fact that they know where the mistake is. They specifically read that paper. It's not very long. And they know one of the proof of one of the lemma seems incomplete.
I guess I heard about that, but yeah. When serious people said there's a mistake, I put it off my mind. But one is not like that. This Joseph Beck paper.
So I have to look at Joseph Beck.
Yeah, I found it. I can even tell you the archive number. Archive 1311.1478 version 2.
Could you please paste it in the comment section that we can look at the paper?
Let's see.
I have one.
I think Fatma already did.
I have already pasted it, by the way.
Okay.
It's in the chat.
Yusuf.
Let's see. I don't know how to use this thing. Yeah.
But it's already there.
Somebody wrote it.
Okay.
Okay. Yeah. Fatima wrote. Yeah.
All right, perfect. I'll look at this one then.
And he says in the paper himself, if you want to check it, I will write me an email and I'll send you the 300-page stuff.
So the paper is not available on archive?
There are two papers. The 70-page thing is on the archive.
Okay.
The other one he sends you if you request from him.
Oh.
That fills the technical details, he says.
But I mean, no one's gonna. It takes so much time these days to check something, really. It gets so technical.
Yeah, he says in this paper, I will read it from, unfortunately, I don't know how to cut the paper to a reasonable size. Neither the assumption of class number 1 nor the Riemann hypothesis seem to make a difference here. If a paper is more than 300 pages long, then it's almost inevitable that there are mistakes. Are these mistakes substantial? Is the basic idea, see section 0 or sections 1 and 5, still good? I don't know the answer. Part 1 includes sections 0 to 6. The reader who is interested in part 2 should send me an email. I will send him or her the PDF file. My email address is this. Yeah, and one of my students sent this email and we got the longer version,
And do you guys have some outline of what is his idea to attack this?
No, I told my student to read it and report it to me, but then he graduated and disappeared. So this is a very typical. I mean, many of my students either went off to data science or whatever, and it's
that's the trend, yeah.
Yeah, they disappear after he started reading it for 10, 20 pages. After that, he disappeared. I thought this is a good thing for a master's
But
student.
honestly, if I thought that I solved the Zigo zero problem, I'll check every detail and I convince people. I mean, that would be a most important result in analytic number theory, basically, if someone does it.
Yeah, I view it as the biggest embarrassment of analytic number theory.
That's true.
I mean, okay, we cannot prove the Riemann hypothesis, but this seems to be such a possibility of a zero so-called one is an embarrassment that's been there for at least 100 years.
Yeah, true.
Yeah.
Invented in these buildings and university. At least the Zigo was working here. I know Gauss wasn't in our building.
First,
Hilbert was,
Lambda who did something. Ziegel did an improvement over it, I guess.
Ziegel has the ineffective bound.
Yeah, but it was this kind of result was first due to Landau.
It was, yes, true, yeah.
Ziegel did later work and got an improvement.
Yeah. Apparently, Ziegel was a very, I would say, maybe angry guy. He would get angry with people very easily. There are lots of stories about him. Yeah.
I've always heard positive things about him. Maybe, who knows? Selberg, I've listened twice. Selberg is kind of difficult person, I should say. I mean, everybody is was so afraid of him.
Oh, interesting.
Yeah, Selberg.
When you guys proved the GPY, Selberg was alive or he already passed?
No, Selberg died well, yeah, initially he was.
Okay.
But there was a workshop in the Institute for Advanced Study. He was dead by then. He died in 2007, aged 90 years old. In the beginning, I think in 2004 or 5, when this result appeared, he sort of in the beginning did not believe it, and then later rumors, these are not like, these are rumors, then later on thought it should be normal, possible or something. But he was by then very old person anyway, over 85.
And the addition that Maynard did to your work that got the bounded came from a comments of Selberg in his lecture note, is that correct? How to change the weight in a way that finished the job.
I've never heard that. I mean, Maynard and Selberg never intersected, I guess.
No, but Selberg makes this comment in his lecture notes about similar way that don't you use that d divide n plus h1 to multiple n plus hk, use this thing instead.
We already pointed out in that paper, there are two ways to improve this result. One way is to go beyond the Bombier-Vinogradov bound. The other way is you change your weights. What Zhang did, he went beyond the Bombier-Vinogradov 1/2 level. And this was worked on by the experts, by Bombieri, Friedlander, and Ivanets themselves. And they declared around 2005 that such an improvement is sort of, I mean, it's again some kind of rumor, but hearsay, let's say. It's a bit more than hearsay in my case, but it's that it doesn't, you can go beyond level 1/2, but not with this lambda von Mangold function. So they declared it impossible, and people gave up because they said so. But
exactly,
Zhang was fortunate in the sense that he wasn't present in these meetings, so he didn't know. So he worked his way. Actually, this sort of thing was kind of predicted or started. They did some work on it, Motohashi and Pintz.
Yeah.
And the Zhang's first lemma, let's say, or proposition is already done by Pintz and Janosch and Yoichi Motohashi.
Yes, that's true.
Zhang did not acknowledge this, and they were kind of pissed off because of this.
They were angry. He wrote on the paper in archives.
But anyway, Zhang did it independently. Now Maynard took the other. Both ways were pointed out in the paper. In terms of certain weights, Soundarajan proved that with a certain kind of weight, our weights were the best. But he has an unpublished proved result like this sound. But Maynard did some other kind of weight, which is k-dimensional.
Yes, so James Maynard told me he took the hint from reading lecture notes of Selberg. I'll email you what part I'm saying.
It could be, of course, but he was Heath Brown's student. And Heath Brown, at some point I read, I guess, or I heard, that it was Maynard who did it completely by himself. I mean, Heath Brown didn't give him the idea.
Yeah, he did it, but he read the lecture notes of Selberg. Selberg makes a comment that I have this upper bound for a number of twin primes. And that's how I get it from my Selberg C. And you can little bit beat my constant, that's the comment. If you use a weight that turned out to solve the bounded gap problem on the Maynard's method. That's the comment.
Yeah, well, one should always read the masters, and Selberg was the master of the...
He was really the person.
I mean, it's my lifelong aim to sit down and read that, but there are several lifelong aims like that, and I never got around doing that. I read many of his papers, Selberg's, but not the second volume completely from one end to other. I didn't read it.
Yeah, he's pretty original, this guy.
Selberg is It's incredible, actually.
Yeah, incredible. Exactly.
Well, maybe in the afternoon there's a guy who's talking on this kind of stuff. Let's see.
Yeah, I read it in the schedule of
Yeah,
the program on the
he
GPY. That's good.
was first my student, then he did PhD with Janos Pintz. I'm not sure if I have some other thing to do in the afternoon, but I don't know what his talk will include. We'll see.
Okay. Right.
Any more questions or comments?
You had
So,
some I guess, in your computer.
yeah, I guess there was some distortion. So, I mean, if there is not any comment or so, I will stop the recording and I will stop the Zoom session. Wait. Semih Özlem has a question. Yes.
Hello.
Yes.
I was mute. Sorry. I think it was called Louisville function lambda.
Liouville functions, yes.
Yes. So does one ever instead say work with some primitive root of unity to raised to some power instead of just -1 to the number of prime divisors?
Okay, primitive instead of -1.
Or would that be because you're concentrating on real quantities mostly, or weighted there, irrelevant, or
If I want to guess, and it's just a guess, that keeping that coefficients may correlate with large value of Dirichlet L functions. If your L functions are like Dirichlet L functions, and the character is defined with the roots of unity, that may work with the Dirichlet L functions. And just a guess, not sure.
Okay. What might be a good place to look at first to understand the arguments that you presented here, maybe, and then to sort of try something like that.
I think that so there was not enough time in the paper. I put much more details, and
Okay.
I look at the variety of measure, like all the variants of whatever we can get from the Liouville. But if you look at my paper, I think it's a bunch of times I give people to read it before putting it in archive, so they check the proof a bunch of times.
Okay. Thank you.
So if there is not much any questions, let's thank our speaker Farzad Aryan once more.
Thank you very much.
And I will stop recording now.